Welcome back, everybody. We're continuing now with a few problems that you know, reinforce the concept of function. Um, Problem 2, determine whether the graph determines a function, then tell the domain and range of the relation. So uh, any picture in the plane is a relation, so there's always a domain and range. The question is whether the thing is a function. Well, this looks for all the world like a line. We can test whether it's a function using the vertical line test. Does any vertical line intersect the graph of the function in exactly one point? And there are several representatives. It looks like every time you draw a vertical line, you're only going to hit this thing once. So we can pretty much declare that this passes the vertical line test. So notice how mathematicians spell vertical line test, because we're lazy. Now tell the domain and the range. The domain is the set of all x's in the relation. So for instance, here is a point that's 4, comma, something. So that means that 4 is in the domain. Likewise, next to it's 4.1, comma something. That means 4.1 is in the domain. In fact, if you keep following the arrowhead out, the arrowhead indicates the line continues forever, there will be x values up to 5 and further. So you can find x values all the way up to positive infinity. Likewise, this vertical line captured an x value which was 3, and everything in between 3. So remember that the domain lives in the x-axis. And if I look vertically from the x-axis, either up or down, I'll find a point. That means that the x-coordinate of that point is in the domain. For this line, I can look up or down and see line everywhere. So the domain of this function is going to be all real numbers. We often abbreviate that in symbols as the open interval negative infinity to infinity. Feel free on tests to use the double bar R to represent real numbers. Likewise, the range is the set of all y's. So if we can find a y coordinate on a point on this graph, then we found an element of the range. So here is a point that's got something, comma 3. That means that 3 is in the range. Well, so is 2.5. So is 2. So is 1. So is everything in between them. You can find a point by going horizontally one direction or the other. You can find a point that's got that y coordinate as its y coordinate. So we could do that for everything on the y-axis. Remember that the function continues down forever, so there is something horizontally across here. So likewise, the range of f equals all real numbers. I'll write that down in words just once to emphasize. And once again, for me on a test, I really don't care which of these you write down. I think my math lab has a preference for the interval notation. Well, here's a function. This is a parabola. You're used to seeing parabolas like this. But this parabola has been rotated a little over 45 degrees counterclockwise. And once that's done, this thing fails the vertical line test rather spectacularly. In fact, every single vertical line intersects this graph in 2 points, except for one special vertical line here. There's a vertical line that intersects a tangent point. And that's the only place where this function passes the vertical line test. Well, you fail the vertical line test if you failed it for one vertical line. So this fails the vertical line test, therefore not a function. Let's call this, since it's a parabola, let's call it relation P. The domain of P, excuse me, the domain of P is the set of all x's. Well, if I start at this tangent point, that's definitely in the domain, whatever that is. Let's call that, oh, it's approximately 4/3. The advantage of a graph is that you can see all the points at once. You get the great picture view. The disadvantage of a graph is sometimes between tick marks you have to estimate. You can never see anything with perfect precision. That's the opposite of an equation. An equation, you have perfect precision everywhere you want, but you have a dickens of a time sometimes seeing the big picture. So the domain can have x's less than we're saying 4/3 equal 4/3. It can't have any x's bigger than 4/3. For instance, 2. There is no point on the graph with an x coordinate of 2. So 2 is not in the domain. The biggest thing we can have in the domain is 4/3. But we can have everything equaling 4/3 or below it. For instance, if you pick -2, you have two choices of points on the graph where -2 occurs as the x coordinate. -2 works everywhere we were intersecting the graph with 2 points. We were picking at an x value in the domain. So the domain is all of this stuff up to and including 4/3. It goes down to -infinity. So the domain would be -infinity exclusively to 4/3 inclusively. Now the range. The range is the set of all y values. Since a parabola has a vertex, you don't often get the range equaling everything, depending on how you orient it. I guess if you actually orient the axis perfectly horizontally, you will get the range being everything, but this one's not. Here at this tangent point is the smallest possible y. And for lack of imagination, I'm going to estimate that that's approximately something -2.1. But then, by using the exact same reasoning we did with the domain, everything above that, we can find a point with that y value. For instance, here, that point has a y value, so that point on the y-axis is in the range. So remember, the range lives in the y-axis. The domain lives in the x-axis. So we're essentially coloring the range in the y-axis. When we get done coloring, then we simply have to write down what we've got. We have the smallest value of -2.1 in the range, and then we go up from there. So we go up and we never stop, so we'd indicate never stopping by saying infinity with a parenthesis. This is what we call, if you're keeping score, a piecewise linear function. It's made up of pieces of lines, hence piecewise linear. Well, I guess we haven't actually determined that it's a function yet, so that's the first order of business. Checking a vertical line, I'll use the side of my straight edge here. So far, every vertical line intersects the function at one point. At x equals -1, it intersects the function at 0 points. The open circles are a standard way of indicating that that particular point is missing. So the point exactly at x equals -1 here is missing, and the point exactly at x equals -1 down here is missing. So we totally missed the graph. Then we're back to intersecting with 1 point, 1 point, 1 point. Here we intersected exactly 1 point. Missing point up here, included point down here. And then 1, 1, 1, 1, 1, 1. So this passes the vertical line test. Therefore, it's a function. Now, we want the domain. The domain is the shadow of the graph on the x-axis. So start on the left. I can get x values of -3. In fact, I can actually assume that value there at that point. I get x values all the way across to, but not including -1. So those are x values for this function. Likewise, I can get x values for all the points on this line segment up here. 1 occurs, and everything down to, but not including -1. Starting just above 1, any of those values here on the x-axis will be an x-coordinate of some point up here. So anywhere I see a point up here, I can drop down. I've got stuff in the domain. And this continues up to and including 4. So I've pictured the domain in the x-axis. All I need to do is write it down. Let's call this, let's just call this function L because it's made up of line segments. So d sub L is going to be, we start at -3, go up to, but don't include -1 because we have a hole there. And then start at -1 and go up to 4. We included both the 4 and the -3 because those were points that were in the domain. We had to exclude the -1. This is probably how my math lab will write it. If you wish, you can use the mathematician shortcut here. What you have is the interval from -3 to 4, and you toss out a handful of things. You toss out one thing. So toss out the set containing -1. My math lab is going to like the top one. I don't care which one you give. I just show you this if you want to save a little bit of writing. I find the second one a little bit easier to understand. I'm taking all that and I'm throwing out what I don't want. Likewise, the range. We start down near -2, but the function does not have a point with a y value of -2. So -2 is not in the range. Everything above it is, at least for a while. All these points here have a y value that would be in the range. And in fact, you can pick y values out of either of these two segments as you come up here. So all this is in the range. You pick up infinitely many possible points with that y of 2, and you keep going up to, but not including 3, because there's no point on the graph with a y coordinate of 3. So your range is -2 to 3. So R sub L is the uncle of Superman. -2 to 3. We put the parenthesis on that because those two endpoints are not included. Now, determine whether this is a function. Well, the easiest way to determine if something is a function is to graph it. And it looks kind of funny. That pi looks kind of crazy. But from what we've done before in algebra, we've graphed lines. That is going to be a slope, and it's positive. So that means the line's going to increase. And that's a y-intercept. -3 is about here with a positive slope. So something about like that. And when we get done with that, we see that everywhere we pass the vertical line test. Therefore, we're a function. And in fact, this will be true for any linear function as long as it's not a vertical line. Any line, as long as it's not a vertical line, will be a linear function. It'll be a function. Often when people talk about using function notation, they're talking about using function rules. So first off, remember that the often used f is nothing more than the name of the function. The x, or whatever symbol you put here, is the input, and the parentheses are just limiting it. They're saying that much is input. The entire thing together we call the function value. Now, if we happen to equate that to something by way of definition, so if we're defining the function, then we call this expression the function rule. It will have multiple copies of the input. I guess it officially doesn't have to have any. In fact, you could have the function rule f of x equals 1. That would be a perfectly valid rule. We call that a constant function because the output is always 1. It never varies. It's constant. To have a variable rule, you have to put copies of the input. And that's what we call function notation.